When you use an AI, it feels like magic, right? You get instant answers, incredible creativity, and it all just seems to happen somewhere up in the cloud. But what's really holding back this revolution? It isn't a lack of ideas or some super complex algorithm. Nope, it's something much, much more physical. So let's peel back the layers and see what's really going on. To you and me, from our perspective, AI is just pure software. We type in a prompt, and boom, a response appears almost instantly. But this totally software-centric view completely hides the massive, and I mean massive physical reality that makes it all possible. Here's the thing. The real story of AI today isn't just about lines of code. It's a story of physics, of electrons zipping through silicon. It's a story about hardware. So what is actually happening in that split second after you hit enter on that prompt? Okay, so let's start by peeling back that first layer. That AI magic we were talking about, it's actually just math. A whole lot of math happening at a scale that's almost impossible to wrap your head around. Every single time an AI model generates a response, it's basically doing one thing over and over and over again. Matrix multiplication, billions, even trillions of times. A single query to a big model can chew through over 140 trillion of these simple math operations. And that, my friends, is a workload that traditional computer processors, or CPUs, were just never, ever built to handle. And this brings us to a huge, fundamental problem in computing. It's called the von Neumann bottleneck. See, traditional computers have a processor, and they have memory, and they talk to each other over a pretty slow connection. To do all that math, a CPU has to constantly go get data from memory, do one tiny little calculation, and then write the result back. This constant back and forth creates what we call a memory wall, where the powerful processor is just sitting there twiddling its thumbs, waiting for data. It's incredibly inefficient. For years, this memory wall was a major roadblock for AI. And then this unlikely hero steps onto the scene, from the world of video games, of all places, the GPU. Okay, so a graphics processing unit, or GPU, is just built differently. While a CPU might have a few really smart, really fast cores, a GPU has thousands, literally thousands of simpler cores. Now, this design is perfect for rendering millions of pixels on your screen when you're playing a video game, and as it turns out, it's also perfect for the thousands of independent calculations you need to do in a matrix multiplication. It was a perfect accidental match. And of course, companies like NVIDIA saw this perfect match, and they just ran with it. They introduced something called tensor cores. A tensor core is a special little part of the GPU designed to do just one thing: perform an entire 4x4 matrix multiplication, that's 64 separate operations, in a single tick of the clock. It's like a purpose-built supercharger just for AI math, a total game changer. So, problem solved, right? We've got GPUs, they've got tensor cores, everything's great. Well, not exactly. As the AI models got bigger and bigger, the bottleneck, it just moved. The real constraints on AI's growth is no longer just the chip itself. And this quote from Lawrence Lundy Bryant just nails it. Chips aren't the bottleneck. Packaging is. It's not about how fast your processor is if you can't get data to it and you can't assemble the final product. The new constraints are packaging and memory. See, here's what's wild. A modern AI accelerator isn't actually one chip. It's a whole bunch of different chips, the GPU, its memory, that all have to be painstakingly put together on a tiny little silicone baseplate. This whole process, called advanced packaging, is incredibly complex and super slow. And that has become the main choke point in the entire supply chain. And on top of that, these hungry chips need a very special kind of fuel: high bandwidth memory, or HBM. HBM is amazing stuff. It's made by stacking memory dies vertically, like a tiny skyscraper, and then placing them right next to the GPU. This gives you insane data speeds, but the manufacturing process is so complex that there's a global shortage. I mean, just look at the numbers here. The world's leading chip manufacturer, TSMC, is trying to quadruple its advanced packaging capacity in just 2 years. That's a frantic expansion, and even with that, they are reportedly sold out all the way through 2026. This right here is the bottleneck in action. And it's the exact same story with memory. In just 1 year, HBM went from being this niche product, about 6% of the memory market, to consuming 20% of the entire DRAM market. That is an explosive leap.
This crazy demand for AI's special memory is creating shortages for everyone else.
So, with this new reality where it's all about packaging and memory, well, that's opened the door for a completely different kind of chip to enter the scene. To get why this is happening, you really have to understand the difference between training and inference. Training is that huge one-time cost to create a model. But inference, that's actually running the model for users like you and me. That is an ongoing operational cost that can be anywhere from 15 to 118 times more expensive than training. And when you're spending that kind of money, every single bit of efficiency matters.
And that is where the AI ASIC comes in. An ASIC, or an application-specific integrated circuit, is a chip that basically gives up all flexibility to do one single thing with brutal efficiency. It can't play a video game, it can't run a spreadsheet, but it can run AI inference at a fraction of the cost and power of a GPU. It's a one-trick pony, but man, it is really good at that one trick.
And when you put them side by side, the trade-off becomes crystal clear. GPUs are awesome and flexible, perfect for research and training new models. But for high-volume inference, an AI ASIC can slash your cost per token by over 50% and be up to 8 times more power efficient. Now, if you're Google or Meta, that translates to billions of dollars in savings. Billions! And this massive economic incentive, it's completely fractured the market. You've got the huge hyperscalers, Google, Amazon, Microsoft, Meta, building their own custom chips just for their data centers. And then you have a whole wave of independent startups trying to compete directly with the big guys. So what does this all add up to? Well, we're in a whole new phase of the AI revolution. This isn't just about software anymore, it is a full-blown hardware arms race, and it has massive geopolitical and economic implications. I mean, this chart right here, it pretty much says it all. While the GPU market is still growing at a healthy clip, the growth of custom AI ASICs is projected to be nearly 3 times faster. The market is screaming for specialized, efficient silicon. And the sheer scale of this shift is just staggering. This isn't some small niche market. It's projected to be worth over $100 billion within the decade, and it's growing at a blistering pace. So let's be absolutely clear about what's happening. What we are witnessing is a multi-trillion-dollar build-out of the world's industrial base. But all of this investment, all of this software magic that we see, it all flows through the physical bottlenecks of advanced packaging, high-bandwidth memory, and the handful of companies like TSMC that can actually manufacture it all. So the next time you type a prompt into an AI, just remember what's going on behind the scenes. It's not just an algorithm floating in a cloud. It's a vast physical factory. And the biggest question for the next decade of AI might not be who can write the best code, but who actually has the capacity to physically build the silicon that it all runs on.